Hi, this is Eric from Astroprecision. For more than a year, we've been delivering the tilt adjuster as a reliable tool for reducing tilt in the Astro imaging stack, excluding the telescope itself. Over the last few months, we've also introduced adapters that allow you to adjust a complete refractor setup. This hasn't been publicly announced yet because we needed a stable TiltAdjuster V2 application, and we wanted feedback from users to confirm how well the solution works. The setup I'll use for this demonstration is my own. It includes the Skywatcher 150ED telescope with a 0.77x reducer, the Player One Poseidon camera, and the Player One Phoenix filter wheel equipped with Barda CMOS optimized filters. And on top, a tilt adjuster with a custom adapter. The tilt adjuster used is the Generation 2 version with a custom adapter for the 150ED. The adapter is attached to the instrument as any adapter. The main difference from the standard adapters is the collimation screws on the top. They help to adjust the angle of the instrument so that the reflected laser can, when rotated, create a circle inside the recorded view. The collimation screws push against the spider vanes from the inside, allowing the instrument to be angled into its optimal position. The TiltAdjuster V2 real-time view shows the laser reflections when the instrument is positioned at the top of the telescope. As you can see, there are multiple reflections. These come from the lens cells, the reducer, and sometimes from the filters and, of course, the sensor. Choosing the correct reflection can be challenging. A simple way to exclude the telescope reflections is to rotate the camera. Only the reflections from the components below the telescope will move. As you can see, only the leftmost large group of blobs shifts position. This means all the smaller reflections inside the circle can be ignored. To be even more certain about which blob to select, you can perform a filter change. Initially, the L filter is selected. When I switch to the S2 filter, which does not allow the laser to pass, the blob I expect to be the correct one disappears. This confirms that the bright blob on the left side is the sensor reflection. When you've identified the correct blob, rotate the instrument to check whether the reflection stays inside the circle throughout a full 360-degree turn. If it doesn't, use the adapter's collimation screws to make adjustments. As you can see here, I've adjusted it so the reflection moves outside the circle. When I rotate the instrument, the reflection is not visible during the entire rotation. This step can be a bit tricky if the lower part of the camera assembly is poorly adjusted. I recommend tuning the lower section until it is close to excellent before moving on to the telescope adjustment. I'll now make the necessary adjustments so the reflection stays inside the circle throughout the full rotation. It's important that all three screws press firmly against their adjustment arms to prevent the adapter from tilting. If you're unable to achieve a full rotation where the reflection stays inside the circle, you can create one by running the wizard. Select the blobs that are visible, making sure the angles between them are appropriate, and include the blob just before it becomes invisible. This will generate a usable circle for further adjustment. Continue refining the alignment until the reflection remains visible throughout the full rotation. I will now run the wizard to measure the tilt. First, I align the adapter with a small mark that I've placed on the dew shield. As you can see, I use the cable clamp, the groove on the adapter, and tape strips where I've marked the approximate alignment points. I've also adjusted the exposure so that a marker appears at the center of the correct blob. It's important that the center is marked to ensure an accurate result. I then sample the blobs using manual mode, where I select the center marker. It's important that the adapter is pressed firmly against the telescope each time you rotate it before taking a sample. This ensures the measurement is stable and accurate. The result is displayed once the full rotation and all samples have been completed. The measurement is then saved so it can be compared with repeated runs. This helps verify stability and ensures that the final tilt result is accurate. I've already done one unrecorded run, and here comes another, so that all 3 runs can be compared. I'll speed up the process. The historic view has now been cleaned up and shows the results from all 3 runs, along with an additional result from a run performed without the telescope. I used the same profile, but I adjusted the distance between the sensor and the instrument so that the calculations remain accurate. First, we can see that the results from the 3 telescope runs differ only minimally. Looking at the tilt angle, the deviation is just 0.0011 degrees, which means the measurements are stable and can be trusted. Comparing this with the result from the run without the telescope, which shows 0.0308 degrees for the current adjustment, the deviation is 0.048 degrees. I let the AI analyze this, and you can read the report yourself. My setup is already good enough as it is, but to show how easily it can be improved, I'll adjust one of the 4 camera adjustment screws and then run the wizard again so you can see the effect. The adjustment screw moves the reflection a bit closer to the center of the circle. I could of course make it even better by tweaking another screw, but I don't think that's necessary to demonstrate what I want. To take the measurement, I run a new wizard round in the same way as shown earlier. As you can see from the new measurement, the tilt angle was reduced from nearly 0.09 degrees to 0.04 degrees. If you ask me, that's quite impressive for just a couple of minutes of adjustment. This brings us to the end of the video. I hope you enjoyed it and that you'll head over to our website and pick up a tilt adjuster with your custom adapter. Thanks for watching.